Let's end our Friday on a positive note, hopefully. End our Friday on a good note, talking about Chapter 16, a new chapter. Okay. Are you guys ready? Can you hear me okay? All right. So Chapter 16 deals with a couple of key points here. Let me just go over some of the topics we will cover. We'll cover acid-base titrations. We will cover KSP, okay, another K value, which is called the solubility product constant. We'll cover buffers. There's a lot to cover in this chapter. And then finally, we will cover the common ion effect. Okay, so those are the four main themes of this chapter, Chapter 16. So let's first talk about the common ion effect. Right, so here is the acid, acetic acid, okay? It's going to react with water to give you H3O plus and acetate ion. So I have a question for you guys. Can you name the acid and the base in this acid-base reaction? Okay, acetic acid is the acid. And what will water be? The base. What will be the conjugate base to this acetic acid? Okay, acetate ion. And what would be the conjugate acid to this base? H3O plus. Yeah, okay, so this is an acid-base reaction where water serves as the base, and this will have a Ka. Okay, so the Ka is about 1.75 times 10 to the minus 5, so that's something you do not have to know. You can look it up in a textbook, and that is the Ka for this particular acid reaction, acid-base reaction, acetic acid. So you can see acetic acid is a weak acid. It's a very low source, a very poor source of H3O plus. Okay, and this is an equilibrium reaction. It's not a strong acid. 1.75 times 10 to the minus 5 is a pretty low number. All right, so this is something that hopefully we have covered in our previous chapter. You could also do a Ka for this, which is products over reactants. Okay, which is acetate ion, CH3COO minus times H3O plus. I'll label it as H plus divided by acetic acid, CH3COOH. Okay. This equilibrium constant is equal to 1.75 times 10 to the minus 5. All right, all of this should be a review from our previous chapter. Now, here comes the twist. We're going to add some sodium acetate to this. Okay, we're going to add some sodium acetate to this acetic acid bottle. Okay, we already know in this bottle of acetic acid, some of it is going to go this direction. Some of it will go and produce this reaction, H3O plus and acetate. But if we add some acetate, sodium acetate, sodium here is a spectator ion, so we really don't have to concern ourselves with it. Okay, it's just there, it dissolves in water, so this is called a spectator ion. But we do have to concern ourselves with is the acetate. Okay, the acetate. So what will the acetate do if you add it to this equilibrium? Okay, like any Le Chatelier's principle, if you add acetate to acetic acid, the common ion here is acetate. Okay, so right here in the box, when we add some of this to this acid that's undergoing this reaction to give us acetate. We add more acetate. We're going to call acetate the common ion. So when you add the common ion, what happens is that this reaction is going to shift to the left. Okay, it's going to shift to the left away. Okay, away from ions. Okay, away from ionizations. Okay, so what the common ion effect does is that it will go away from the side that has ions. In other words, it will suppress ionization. So equilibrium will shift to the left, away from the ion H3O plus and away from the ion CH3COO minus. So shift left, away from the ions. Okay, in other words, it suppresses ionization. Okay. So what should us as a class know about the common ion effect? You add a common ion, it will move to the side away from the ions themselves, so we suppress the ionization. Okay? We'll make more acid. Okay? So common ion effect, suppress ionization. Okay? Prevent ionization from happening. That's all I'd like for you to know. Now let's talk about something called KSP here. Okay, let's go to page 2 of our notes. So adding the common ion, adding this to this by Le Chatelier's principle moves it to this side. Okay, it moves it to this side. So adding the common ion, okay, here, we'll move it to this side. All right, now, so common ion effect suppresses ionization. Let me introduce to you a new equilibrium constant here. This is called KSP. Okay? KSP here. Okay, so the SP in KSP stands for solubility product. And we're going to use KSP for a solid. So we're going to use it specifically for a sparingly soluble solid. Sparingly soluble solid. Okay, so what does a sparingly soluble solid means? It's a solid, but some of it gives you ions. Okay, some of it gives you ions. Okay, this is an example of a sparingly soluble solid. So when you do the KSP, you're going to have a solid on the left-hand side. You're going to have a solid in the reactant side. Okay? It's in an equilibrium. Okay, how do we know it's in an equilibrium? Because of the back and forth arrows. And it is at an equilibrium with its ions, corresponding ions. Right, so what will the KSP value for this be? Okay, well, we can get the actual numeric value from our table or from our textbook, but the expression is going to be concentration of products over reactants. Okay, what do we do with calcium fluoride as a solid? Does that go into our KSP? No. Okay. And for this specific example, the sparingly soluble solid calcium fluoride, okay, what do I need to put here? Okay, I need to raise it to the power of 2. Okay, why do I need to raise it to the power of 2? Okay, because there's a 2 as the coefficient. All right, so that is the KSP Now, if you go in our notes, I think somewhere on page something. Anyways, we can look up the value for this in our textbook. I don't have that in front of me right now, but that's okay. But this is the equilibrium expression. Calcium ion plus fluoride ion is in an equilibrium with this solid. Okay, so anytime you see a solid that's in an equilibrium with its ions, we're going to use KSP because calcium fluoride is a sparingly soluble solid. Okay, some of that solid will go back. Okay, some of that solid will go back into its ions. All right, I'm going to write the I'm going to write this equation one more time. Okay, don't forget to balance it. So for our ice table here, we will not use X. Okay, we will not use X, we'll use S. All right, so this will be, now we don't care about the solid. Okay, this will be plus S, the amount that goes this way, and this will be plus 2S. Okay, plus 2S. So here the S stands for solubility. It's just like the ice table, but in the ice table you used an X. This also is an ice table, but we will not use X, we will use S, because the S stands for solubility. It's an ice table, but we will use S. Okay, the S, like I said before, stands for solubility. How much of that solid goes back dissolved into liquid? Just look up something here just for a second. All right, so now our KSP here is going to be the concentration of products over reactants. Okay, squared. Okay, what is calcium ion in solution as some of the calcium fluoride goes back the other way? Okay, it's going to be S. Okay, what is the fluoride ion concentration as some of that solid goes back into ions? What will it be? 2S. Okay, so this KSP is going to be S times 2S, and then we got to square it. Okay, so our KSP here is going to equal to 2S whole squared is 4S squared. 4S squared times S is 4S cubed. Okay. So if you go on page 12, and I know it's very hard to see, but that's okay. I'll give you all of these constants on the exam. Okay, the KSP is, for this one, is about 4.0 times 10 to the minus 10. Okay, this is what I get from the textbook table. Okay, so you don't have to know that. So that's the KSP value, so you can plug that in here. Go ahead.
Is it 4S cubed or 4S to the 4? S, 2S. 2S squared is 4S squared. 4S squared times S is 4S cubed. Yeah, good. Yes, okay, good call. 4S cubed. Yeah, make sure you know the math here. Okay, so it's about 4.0 times 10 to the minus 10. Okay. All right, equals 4S cubed. So let's figure out the solubility of calcium ion and the solubility of fluoride ion in this KSP. Okay, so we're going to take and solve for S. It's going to be 4.0 times 10 to the minus 10 divided by 4, and we got to cube root it. Okay, cube root it. Okay, this is how we'll do our KSP problems in this class. Okay, do you guys know how to cube root on your calculator? Okay, some of you do. I think Michael says he does. For those of you that don't have easy access to that number, you can also do this
to the power of 1/3. Okay? If you don't have a cube root, you can do it to the power of 1/3. Right. So 4.0 times 10 to the minus 10 divided by 4 is 1 times 10 to the minus 10. Okay, we'll cube root it, and to me, I'll just take it here. I'll take it to the power of 1/3. So I'm getting about 0.000464 molar. Okay, what is that? Okay, that is S. And what does that S symbolize? Okay, it's going to be the concentration of calcium ion. Okay, and it'll also be the concentration of fluoride ion. Okay, times 2 though. Right, 2S. So how much of this calcium fluoride goes back here to give you calcium ion dissolved in water? Okay, so the calcium ion concentration is going to be 0.000464 molar. And then the fluoride ion concentration is going to be that, it's going to be times 2, because you give me 2 moles of F minus. So what's 0.000464 times 2? Okay, 0.000928 molar. Okay. So if you have solid calcium fluoride, okay, let's say you make 1 liter of it. Okay, let's say you're trying to precipitate 1 liter. Okay, some of that solid that you participate in, this 1 liter, will go back and will give you dissolved calcium back in water at a concentration of 0.000464. And some of it will go back and give you, will dissolve as F minus, and that F minus concentration will be 0.000928. Right, so this is how we do our problems here. Okay. This is the KSP problems. All right, let's do one more KSP here. Let's do calcium phosphate, another example of a sparingly soluble solid. Okay. So it turns out calcium phosphate is a solid, and some of that calcium phosphate as a solid goes out back into solution. Okay, so this solid, anytime you see a solid and an equilibrium sign, okay, that means it is KSP. So some of that goes back as calcium ion, and some of this goes back as phosphate ion. Let's go ahead and balance this. We have 2 PO4s, and then we have 3 calciums. So I have the KSP for this. I looked it up before class, and I'll give you these constants, so you do not worry about it. It's 1.2 times 10 to the minus 26, so that's given. Any type of constant will be given to you. Okay. All right, we're going to do the same thing as we did before for calcium fluoride. Okay, because this is a solid in an equilibrium with the component ions, we'll do an ice table, but instead of using X, we will use S. Okay, some of that solid will go this way, and instead of 1S, how much S should it be? Okay, it will be 3S because we have 3 calcium ions. And how many phosphate should it be? Plus 2s, okay? Right, our equilibrium expression is KSP is equal to calcium ion to the power of 3, okay, divided by PO4 minus 3 to the power of 2. Okay, where does the square come from? It comes from the fact that we have 2 PO4s. And where does this 3 in the cube come from? Okay, it comes from the fact that we have 3 calcium ions as this goes back. Okay. Right now let's plug it in. Okay, the calcium ion will be 3s. Okay, this will be 2s. So our KSP is going to equal to 3s cubed. Let's plug that 2s in there. 2s squared. Okay, this may be a little tricky. It's a little math heavy. Okay, what is 3s cubed? 27s cubed. What is 2s squared? Whole squared. 4s squared. Okay. Let's go to the next sheet here. All right, what's 27 times 4? 27 times 4 is 108. And what's s cubed times s squared? Do you remember how you do this, Michael? When you add the exponents. So what will it be? S cubed times s squared? S to the power of 5. Very good. Okay. So we know our KSP here is 1.2 times 10 to the minus 26. All right, this time we're going to take the s to solve for s and isolate s. We have to take the 5th root. Okay, not the cube root, not the square root, but the 5th root, okay, to get our s, right? So these are the type of problems we will encounter in our homeworks. Another way you can take the 5th root is you can do this calculator. You can do this fraction on your calculator and compute it, and take that answer and raise it to the power of 1/5. Okay, that's another way you can do that. Okay, these two will give you the same answers. All right, so. All right, so I'll do it this way because it's a little bit easier for me. But you can use the 5th root here, right here, this number on my calculator. Okay. X square root. But I'll do it this way. So 1.2 times 10 to the minus 26, which is the number that I got from the textbook. Okay, divided by 108. Okay, that's my answer. I'm going to raise it to the power of 1/5. I'm getting 2.5 times 2.56 times 10 to the minus 6 molar. Okay, so my solubility is 2.5756 times 10 to the 6th molar. Okay, so what does that S represent? Okay, that S represents, let's go all the way back to our ice table. Okay, it represents this concentration of calcium that's coming from the reaction going back. So we'll need to multiply it by 3. And then it represents the concentration of phosphate from the reaction going back. We'll multiply that by 2. Okay. Right, so finally the solubility of calcium ion is going to be 2 times 2.56 times 10 to the minus 6. And what is that? That's going to be 5.02. 5.12. Times 3, right? Oh, sorry. Okay, the solubility of calcium, we take that S and multiply it by 3. So 3 times 2.56 times 10 to the minus 6.
7.69, 7.67 times 10 to the minus 6. And the solubility of PO4 minus 3 in calcium phosphate, the amount that goes back into solution, the amount that dissolves back as this reaction goes this way, is going to be 2 times the S. And that is 5.12 times 10 to the minus 6 molar. This is how we do these types of problems. That is to say, if we were to precipitate out calcium phosphate, let's say we try to get a liter, try to precipitate a liter out of this, okay? 1 liter out of that 5.1 times 10 to the minus 6 moles over that liter will come into dissolve back this way, and 7.7 times 10 to the minus 6 will go back and dissolve as calcium ion. Okay, 7.7 micromolar and 5.12 micromolar. Micros 10 to the minus 6. All right, so that is how we'll do a sparingly soluble solid. So those are 2 examples of sparingly soluble solids. Those are some examples of KSP. Let's now go into, we'll do more. Trust me, we'll do a lot more. Let's just shift gears before we come back to KSP. There's an equation here I'd like for you guys to know. And this is kind of shifting gears, so to speak. This is the Henderson-Hasselbalch equation. Okay, Henderson-Hasselbalch equation. And I'll give this to you on the test, and you do not have to derive it. But it's pH is equal to pKa plus the log. Okay, if you're memorizing this on any exam, which for my exam you don't, but let's say you need to use this, you need to remember it. The way you remember it is drop the acid. Okay, drop the acid. So the acid goes in the denominator. And then the conjugate base goes up above. So we will use this whenever we talk about buffers. Okay. So there's a very interesting history of Henderson-Hasselbalch. So in Harvard, these two were not they were physiologists, they were doctors. Okay, and they were studying physiology. And Hasselbalch has a hall in Harvard. It's called Hasselbalch Hall. Just like this is Hendricks Hall, Hendricks Science Building, there's Hasselbalch Hall. And he was the one that came up with this equation along with Henderson. And they were actually working on heart, muscle. Anyways, they were doing medical research, and that's how they came up with this equation. Here in Gen Chem 2, we will use this equation when we're talking about buffers. Okay, so what is a buffer? Okay, a buffer is a combination of a weak acid and its conjugate base. Okay, and what will a buffer do? What is its ultimate function? Okay, what is an ultimate function of a buffer in our bodies? Okay, the ultimate function of a buffer in our bodies or in any solution, if you're going to make a buffer, is to keep the pH steady. Okay, you do not want your pH to go too high or too low. Okay, too high or too low. So, in our blood, if your pH or blood pH is below 7.4, that's acidemia. Okay, and that's not a good thing. If your pH is above 7.4, that's alkalinemia or something. It's too basic. You want to keep it 7.2, 7.3, 7.4, that within that range. Okay, so in order to do that, you have a combination of an acid and a base. So if there's too much acid, the base in your buffer will eat it up. If there's too much base, the acid in your buffer will eat it up. So the buffer, the best buffer, is a combination of a weak acid and its conjugate base.
this is what a buffer is. Okay, why do we want to have a buffer, or what's the point of having a buffer? It's to keep the pH from wildly going out of control. Okay, that's not something you want. You don't want, think of your body, okay? You don't want the blood to go too acidic, you don't want it to go too basic, okay? Right? You know, when they test your urine, the clinical chemist tests your urine. If it's acidic, that's going to be a big issue. It's going to raise red flags to them, probably, you know, acidemia. If it's too basic, that will raise red flags. Something is wrong with your body. Okay, so buffering and buffering capacity is basically you want to keep the pH steady. Okay, and when I say steady, maybe plus 1 pH unit. Okay, if maybe that's even too liberal, but you know, you don't want it to go from, you know, too high or too low. Okay, so actually, you know, 0.1, 0.2 pH units. Okay, 1 whole pH unit is a lot in our bodies, or any type of buffer. Okay. So a buffer will keep the pH steady. Okay, keeps the pH steady. Okay, and this is the equation that we will use anytime we have a buffer. So how do you know you have a buffer? Okay, what makes a good buffer? Okay, you have some of this, and what else will you have in the beaker? Okay, some of what else? The acid. Okay, anytime you see in your problem you have a little bit of A minus, and anytime you see in your problem you have a little bit of HA, go ahead and plug it into this equation to get the pH. Okay, because now you know you have something that's a buffer. Okay. In real life, a buffer keeps the pH steady, and it's, like I said, it's a combination of a weak acid and its conjugate base. All right, so sparingly soluble solids, KSP, we kind of touched upon it on the surface. We talked a little bit about the common ion effect, how it will suppress ionization. We have an equation here for buffers, which is a weak acid and its conjugate base. I'll give you this equation on the exam. And let's see what's going on here. Okay. And let's do a practice problem here that involves this sort of thing. This equation. All right, so part A should be a review, but we'll do it anyways. What is the pH of a 0.3 molar solution of formic acid, HCOOH? Okay, so if you have this question on the exam, can you be able to tackle it with a lot of confidence? Okay. Part A is a review, so we'll do it really fast. Part B is where we will use our Henderson-Hasselbalch equation. But first, part A, okay? First, we're going to write our equation. If you're given this on an exam, okay, what is the pH of 0.30 molar solution of HCOOH? First thing you do is write the equation. Okay, this is a review. Okay, the second thing is you make your ice table. Okay, this is not a sparingly soluble solid. Why isn't it a sparingly soluble solid? Do you see any solids here? Okay, instead this is more of an acid-base equilibrium. All right, so 0.30. We do not care about the liquid. This is 0, this is 0. Okay, some of this bottle of HCOOH will give you formate ion and proton. Okay, so this should be clockwork for you guys now. Okay, hopefully, if not, practice over the weekend these types of problems from Chapter 15 and the Chapter 15 homework. Okay, we'll plug this into our equilibrium expression. The Ka for formic acid is something I'll give you, so don't worry about memorizing that. But the Ka for this formic acid is 1.8 times 10 to the minus 4, and that equals to products over reactants. All right, we know at equilibrium this will be x, and that will be x, and this will be 0.30 minus x. So x times x is x squared. 0.30 minus x is that. This is equal to 1.8 times 10 to the minus 4. Okay, then we're going to use our low ionization assumption. Yes, you want it. Okay, so we will assume x is small. So 0.3 minus x is about 0.3. All right, so let's solve for x here. And what do we get when we do that? 1.8 times 10 to the minus 4. Times 0.30. Square root that. Oh, how did I do that? .00734. 735. Okay, so this is our answer. Okay, so what does that x represent? Okay, it represents this x, which represents the concentration of H3O plus, and then we can solve for the pH because pH is equal to minus the log of H3O plus, which is minus the log of 0.00735. And what is that on our calculator? .13. All right, so this is something that we've done in Chapter 15. It's something that we have done in our homework, and it's hopefully a good review. But now let's look at part B with me here. Okay, so now we have the pH of 0.30 molar formic acid, which is HCOOH. Okay, but now they've added some 0.52 molar potassium formate. Okay. So when you add potassium formate to this, you have a common ion. So what will our common ion be in part B? Okay, it's going to be this 0.52 molar formate, and what's the other common ion? Okay, the formate from this 0.3 molar formic acid. Okay. So shown in pink is the common ion. Okay. When you add some potassium formate in there. Okay, so would be the common ion. Okay, what will the common ion do? It will suppress ionization. It will force the reaction to go this way. Okay. Okay, so here we have the 0.3 molar formic acid giving us formate. We have the 0.52 molar potassium formate being a source of formate. That is a common ion. Now instead of doing two ice tables here, I know you guys don't like ice tables. Okay? Instead of doing two ice tables, we can actually go ahead and put it into our equation for the Henderson-Hasselbalch.
Okay, why can we put it into this Henderson-Hasselbalch equation? Because we have the presence of the acid, and what else do we have a presence of? The conjugate base. Very good. Okay, so let's put that into the equation, and we avoid having to do, a complicated isotope like we did. Okay. So if you have the conjugate acid and the acid together, like in this problem, you can just plug and play into the Henderson-Hasselbalch equation. All right, so the equation, once again, is something I'll give you on the exam. Okay, if you're in a situation where you need to memorize this in a hurry, just know, drop the acid. Okay, drop the acid. All right, so pH is what we want to find. The pKa is minus the log of Ka. And what is the Ka? Let me look that up. The Ka here is 1.8 times 10 to the minus 4. Plus log. Okay, what's the concentration of formic acid? Concentration of formic acid, HA is 0.30. And what's the concentration of the formate? 0.52. Okay, formate. Okay, what is the potassium doing here? Is it doing anything? Okay, the potassium, this is common comment that students make. Oh, what about the potassium? What about the K plus? Or what about the Na plus? Or what about any counter ion? It doesn't participate in any acid-base reaction. Anything that participates in the acid-base reaction is the HCOO minus coming from the HCOOH. Okay, so this is just what we call a spectator ion or a counter ion. But anyways, this is 0.52. Do we know how to do this on our calculator? Okay, so this will be minus the log 1.8 times 10 to the power of minus 4, 3.74. I'll put some extra digits here. Okay, plus the log of 0.52 divided by 0.30. Okay, log of that plus 0.23, 0.239. Okay, and when I add those up, I'm getting about 3.98. Yeah. Right, so this equation definitely is a lifesaver, okay? And this is a buffer, okay? The buffer is containing formate and formic acid. Right. Right, we got another 5 more minutes here. Calculate the pH of 0.2 molar acetic acid. The Ka here is 1.75 times 10 to the minus 5. So you can do the low ionization equation and go ahead and solve for that. It's basically the same thing that we did for formic acid. Okay, this is just 0.2 molar acetic acid by itself, so we'll do an ice table. Okay, water is a liquid. We do not concern ourselves with it, so this would be minus x plus x.
just like before. Okay, we'll plug it into our equation. Okay, products over reactants. So this is going to be x times x squared divided by 0.20 minus x. Okay, we can use the low ionization assumption because 1.5 times 10 to the minus 5 is a small number. So we'll assume x is small. So this will be x squared divided by 0.20 equals 1.75 times 10 to the minus 5. And what do we get on our calculator when we do this? Getting 0.00187. So make sure you are comfortable doing this. Okay, we are assuming x is small, which is, a fair assumption. We got our x, but what does this x really symbolize? Okay, this x is the concentration of acetate ion, but it's also the concentration of H+. Okay, so from that we'll get our pH. pH is equal to minus the log of the hydroammonium ion concentration. So what's minus the log of 0.00187? 2.73. This is our answer. But what happens if we take that bottle 0.2 molar acetic acid and we add 0.3 molar acetate? So what is our common ion here? Okay, the common ion is going to be acetate. And this common ion of acetate, by our addition of 0.3 molar acetate, will shift this equilibrium to the left. It suppresses ionization. It goes to the side away from the ions. Okay, what's a good equation we can use to solve for the pH when we add these two together? First of all, what do we have? We have the acid, we have its conjugate base, so we have a buffer. Okay, so we can quick and easily plug it in to the Henderson-Hasselbalch equation. pH is equal to pKa times the log. Okay, we'll drop the acid. pKa is minus the log of Ka. So I'll give you this Ka for this acid. I'll give you the Ka for any acid. All right, what's the concentration of acetic acid here? 0.2. What's the concentration of the acetate ion? 0.3. And this will be our answer. So minus the log 1.75 times 10 to the minus 5, about 4.76, plus log of 0.3 divided by 0.2. 0.3 divided by 0.2 is 1.5. So log of that is 0.176. It's about 4.93. 4.93, 4.94. So
this is the common ion effect. The common ion here is acetate, okay, causing it to move away from the ions, the side with ions, and giving us more of the acid.